This seems to be an interesting problem. This is from the JEE Advanced 2020 Physics Paper 2. And it says that a beaker of radius r is filled with water, which has a refractive index of 4/3, up to a height h, as shown in the figure on the left, so this one. The beaker is kept on a horizontal table, rotating with a speed, with angular speed omega, all right? This makes the water surface curved so that the difference in height of water level at the center and at the circumference of the beaker is h. H is much less than r. H is much less than capital H, and h is also much less than the radius r, as shown in figure on the right. So this one. Take the surface to be approximately spherical with radius of curvature r. Which of the following is or are correct? G is the acceleration due to gravity. All right. So this is a spherical surface, this one, and since it's a part of the surface, it might make sense to actually draw that sphere. Let's say this is the center and this is the radius curvature r. Now let's first figure out what r is. So what we basically have here is a cylinder. So this radius is r, and the point where this line intersects the end of the beaker, the boundary of the beaker, that is to say. Let me draw a better line here so that I can illustrate it better. So this is just the radius. So this is r. This is a 90-degree angle. Why? Because, well, it's the radius, so it comes out axially it comes out perpendicular to the axis, and this length right here is r minus small h. Well, as simple as that. Now this is a right angle triangle. We know what r is. We know what r is. We have to figure out capital R, and we know what r is, and we know what h is. So let's do that. So r squared is equal to r minus h squared plus small r squared. This is by Pythagoras theorem, by the way, or Pythagorean theorem, as you may like it. And if we just write that in a bit more cleaner form, so that we can solve for r plus r squared h, and really easily we can see that capital R is equal to h squared plus r squared divided by 2h. So option A is correct, B is not correct. Now let's look at option C and D. Now, the apparent depth of the bottom of the beaker is close to this. Now, this is interesting. How do we figure this out? So, both of these options, by the way, are just about apparent depth of the bottom of the beaker. So what we have here right now is a sphere. And as it is rotating, you don't really see anything but a spherical surface with a radius of curvature of r. And if I just erase these things, we don't really need them now. And since it's a sphere, since this is a sphere, this can act as an optical instrument, so it can bend light. So any light that let's say find its way from here, let's say it goes onto something like this, and it then gets, well, I should have probably drawn it in a better way. Let me draw it like this. So something like this, and then since this is a rarer medium, air is a rarer medium, it refracts away like this, and we have two light beams coming in like that, and then you do something like this, and you get a different apparent height, that is to say. Well, how do we figure out what the image is? So basically, now the problem has boiled down to a spherical surface that acts as an optical instrument. It separates two mediums. So the upper medium is air, the lower medium is is water. It has a refractive index of 4/3. And you have the object. The object is the base itself. So the base is the object. It is at a distance of h. Now, you might as well say it is at distance of h minus h or something like that, but that doesn't really matter since h, the small h, is much smaller than capital H. So the object distance is capital H. The radius of curvature of this optical instrument, that is equal to capital R. All right. And we need to find the image distance. Well, that's really easy. That we just need to plug this into the regular formula when we have any refraction from curved spherical surface. So the formula is mu divided by v. This is the object distance. Everything has to be with the sign convention. Minus 1 upon u is equal to mu minus 1 divided by or I should write this as mu, the mu I, relative mu, or anything, I don't know. This divided by the radius of curvature in this case is positive r, because incident light goes in this direction, the radius of curvature in that direction as well. So positive r. What is the relative index? The relative index is 1 upon 4/3, that is 3/4. So you have 3/4 times v minus 1 upon. Notice that this image distance is minus h, since it's opposite to the incident beam. So it's negative h. So negative h is equal to 3/4 minus 1. Let me just write that as 1/4r. And now we can write this as 3/4v is equal to negative 1/4r minus 1/h. Since these get canceled out, you have a plus, and then you take it that side, you get a negative, and so on and so forth. What else? We can now write this as let me just simplify this a bit more. So this will be negative h upon plus 4r, all of this divided by 4rh. These 4's get canceled out, and what you're left with is that v is equal to negative. Notice the negative. That means the image is forming behind the mirror, so it is a virtual object. It is a virtual image. We knew that has to be the case. So v is equal to negative 3rh over h plus 4r. So that's where we stand now. But notice that the options don't really involve r. They just involve h, and they involve omega. So what do we do now? One thing we can do is try to apply some fluid mechanics and figure out if we can probably find a way in which we can relate omega and g and r, or some other form. So let's try that. So if we notice right here, if I draw the curvature again, if the option had been in the form of r and h, we would have been done by now, but since it's not, it wants us to do a bit more of work. So this is the surface, and let me just assume a small cylindrical bit of water. I draw a free body diagram for the fluid. It's a bit of problem visualizing that, how we can do that, but it just works. Take my word for it right now. The depth of the end is h. The depth here is 0, so we're not considering that. The pressure that the fluid applies here, let's say it's P naught, and let's say the pressure that it applies right here. Notice that P naught is due to just atmosphere. So the pressure right here on this end is P naught plus rho GH. Now, if let's say the cross-sectional area of this tube is capital A, let's say delta A. be better. And let's say it's delta A, and the length of this is just the radius. So that's just the radius r. So the mass of this volume, is rho times delta A times r. This is the mass of this volume. And it is going around this axis. It is going around this axis at an angular speed of omega. So that means it has a centripetal force on it that makes it do that. And the centripetal force for a distributed mass system is applied at the center of mass of it. So the center of mass is exactly at the middle. So it's at a distance of r by 2. And the centripetal force, well, that is mass times omega squared times L. L is the distance, the point of application of the centripetal force. So this is the mass times omega squared times L by 2. So r by 2, sorry. R by 2, that's what I had to write. R by 2. This is the centripetal force. The cause of the centripetal force is just the difference in these two pressures, forces due to pressures. So the difference in these is rho gh multiplied by delta A. So cut the delta A's out. That is done. Cut the rho's out as well. That is also done. And what do we have? We have omega square r squared by 2 is equal to gh. All right. That seems to get us somewhere. And what else can we do? Let's try bringing in the other component. The other component is this. This is the other equation that we have. So the other equation that we have that we just found out is r is equal to h squared plus r squared divided by 2h, right? Now we need to invoke this here, and here's where the other bit comes into play. H is much lesser than r, the radius. So this can very well be written as r squared over 2h, since h squared is abysmally small compared to r squared. Good. This is a bit of work. So small h is equal to r squared over 2r. We just do a cross multiplication thingy right there, and then we put everything right in here. So you have omega square r squared divided by 2 is equal to gr squared divided by 2r, and r squares get cancelled out, and so you're left with r being equal to g over omega squared. I could have probably done that in an easier way, but anyways. So we just plug this in, right? So let's first separate the h component out of this. So this gives us 3h multiplied by 3r divided by h plus 4r, right? We can probably factor this 4 out as well. So that will give us 3h by 4 multiplied by 3r, and here you have h by 4 plus r. All right. And what else can we do? And we can also cancel the r's as well, right? We can do that. So we can write this as, let me do that right there. It's 3h by 4. Notice there is the negative sign. That just means depth. It's just the opposite of the incident light ray. So 3h by 4 multiplied by 3r, and then h by 4 plus r. This can be written as 3h by 4, and then you have h by 4 plus r divided by 3r, and this you have a negative, you have an inverse sign right there as well. Oh, I probably have committed a serious mistake right there. There is no other 3. I don't know why I did that. Sorry. Anyways, so we now have 3h by 4, and then 1 plus h by 4r inverse, and then we now use this. So we now put everything right here, And so this gives us 3h by 4, and then 1 plus omega squared h over 4g, this to the power negative 1. So this is this option. So this one's wrong again. So this took me probably longer than I would have wanted to spend on this problem, but that was because, well, it involved lots of concepts at once, but this was a nice problem.